Ooh, maybe. There we go. And then, so the first thing I always do is like read through the whole problem and ask myself, like, what the heck am I trying to find, right? So we want to find the dimensions, so like a length and a width. So width, length. But then we want, here, Elijah, notes. We want the specific length and width that are going to maximize the total area. So when I see the word maximize, I think vertex. And then I have to ask myself, like, what function am I finding the vertex of, right? So whatever function it is I'm trying to maximize, that's the function I want the vertex of. So if I'm maximizing the total area, that tells me I need an area function. So make sure that you're like writing and using the appropriate function for this, right? There's all sorts of functions we could write for like length, for perimeter, all these things with respect to a rectangle, but we want to make sure that we're writing the function for that has an output, which is actually the thing we're trying to maximize here. So that tells me I want an area function, so we're going to say my area is a of x. This is my output. And then as far as what thing I label x, I mean, it doesn't actually matter. Like you could choose either way, but I always find it easiest to label the thing that's used most often x. So like we have like 5 vertical segments and only 2 horizontal segments. So I'm going to label the vertical segments x because that's used more. It just makes it easier to solve for the other one. So x, ooh. X, and that's going to be my width. So this will be the input of my function. I know that's going to be the input of my function because I said my area was going to be a of x, which means it uses an input of x. Oops. So then I will label my length. I'm just going to call it y. You can use other variables, like you can use w and l, but be careful that you're not like writing like w equals x and then using w sometimes and x sometimes. Like don't define a variable in terms of a variable. Like if you want the width to be w, say width equals w and then use w as your variable, that's totally fine. But if you say like w equals x, then you have 2 variables kind of for the same thing and no words, and it's easy to get things all mixed up. So my length I called y. And I can say my area, so a of x, is equal to length times width. So that's true. But then I run into trouble because my area has to be a function of x, which means that the formula can't have any other variables in it. So we can't have a y here. So that's my clue that I need to somehow express my length in terms of x. So that's where I'm going to use the fact that we only have 600 feet of fencing. So the total amount of fencing used, well, I have 5 vertical segments, so 5x, and then I have 2 horizontal segments. Whoa, I said 2, I wrote 5, 2y, and all of that together has to be the 600 feet of fencing that I have. And I want the length in terms of x, so I'm going to solve this for y. So we have 2y equals 600 minus 5x. So y equals 300 minus 2.5x. And it's totally fine to use a decimal here because it's a terminating decimal. Like if that had been like 0.3333 repeating, I would have left it as a fraction. But If we can write it as a decimal that actually ends and is exact, that's pretty convenient because then we don't have to mess around with fractions. So that's my length. I'm going to fill that in over here, 300 minus 2.5x. And so now I can replace y with 300 minus 2.5x in my area function. So my area function is a of x equals x times 300 minus 2.5x. We'll go ahead and distribute. So negative 2.5x plus 300x. Oh, sorry, that's squared. X squared. Hello? Oh, there it goes. So now that I have my function, we know that this function opens down because a is negative, right? So the leading coefficient is negative, which means it opens down. And so the vertex is going to be my maximum. And so I'm going to find the vertex in order to maximize my area. So remember what this looked like visually. Like, we don't have to use the graph to actually solve these now that we have algebraic ways of doing it, but it's a good idea to keep it in mind, right? This is going to look like something like this. This is the point we're looking for. So vertex is where area is biggest. If this is a of x and this is x. So we're going to find the vertex. So remember, the x coordinate of our vertex is given by that negative b over 2a. So negative 300 over 2 times negative 2.5 gives me 60. What did I just find in terms of the problem, like in terms of the rectangle?
The length of each x?
Right, so yeah, it's the length of each vertical segment. So we called that the width. I don't really care what you call it, but as long as you're consistent. So yeah, we just found the width, but we found a specific width, right? We found the width that's going to make the area a maximum. So this is the width that will maximize the area. Well, what do I want? I want dimensions, which means I need a width and I need a length. It's not asking me for the area, so I'm certainly not going to plug this into the area function because I don't care what the area is. I just care that it's at a maximum. So the dimensions are the length and the width, so I'm going to go back up to my list and say, oh, length is 300 minus 2.5x, and I know what x is. So length is 300 minus 2.5 times 60, which I believe is 150. Sorry, I'm running out of room. So this is not organized super well, but so the dimensions that will maximize area are 60 feet by 150 feet. And again, you just want to kind of take it nice and slow through every single step and ask yourself what you're trying to get and what is going to get you there, right? It's easy to go on autopilot and get an X value and throw it into your A of X and spit out a number, right? But if we slow down and think about what we're trying to find, if we're trying to find length, it doesn't make a whole lot of sense to plug something into our area function, right? So if the area function gives you area and we want length, we certainly wouldn't want to use the area function to find it. So just if you just slow down and think really carefully through what it is you're actually trying to find, I think that you guys do just fine of like picking what's going to get you there. You just don't want to like start rushing through it and just plugging things in like crazy. Any questions on this one? So as far as knowing what I was supposed to do at any given point of this, so remember the first thing we did was just ask ourselves what it was we were trying to maximize, right? And that told me I needed an area function because I was trying to maximize area. And so that's why I chose something to represent my width and then figured out how to represent my length in terms of that. Because if I want to write an area function, I need something for length and something for width. So always start with what it is you're trying to maximize or minimize, and that's going to tell you what function to write, and then how you write that function determines what other pieces of information you need. So far, so good? Okay, let's do the store thing. So, like, this part of the problem I want to mention is, like, I put on here just to, like, kind of lead you through the pieces that you need to answer the actual question. So, like, if you have a question like this on the test, it's just going to ask the question at the bottom. It's not going to lead you through every single step. But in order to get there, so in order to maximize revenue, we need to have a revenue function, which means we need to multiply price times quantity, which means we have to express both our price and quantity in terms of our input. So that's what that bit at the top is just going through. I think that the simplest way to set these particular ones up is by using just a little table. So notice that this is a situation we've been in before. We're talking about the relationship between price and the quantity demanded. But instead of having X represent either the price or the quantity, in this case, X is going to be the reduction in price. So the change in price as opposed to the price itself. This is a little bit different than what we've done before, but it actually makes this easier to set up and solve if we think of it this way rather than if we make the price itself our input. So I'm going to just make a table. And let's see. So I've got two things going on here. I've got price and quantity. So, and we have sort of like the starting price and quantity. And then one of them is going up and one is going down. By some amount, so that'll be the change. And all of that is going to give me like the new price and quantity based on X. So, well, let's see. What are we starting with? Well, it tells us that at a price of 100, we can sell 400 coats. So our starting price is 100 and our starting quantity is 400. And then I have to figure out which of these is going up and which is going down. So which is it? Is the price going up or is the price going down? It's going down, right? Because we're told that for each $1 reduction in price, 8 more coats is sold. We're also told, just by the way we defined our variable, that it's the reduction in price. So price has to be going down. So this is subtraction, which makes this addition. You will always have one of each. So as price goes up, quantity goes down, and vice versa. So once you decide if one is addition or subtraction, the other one has to be the opposite. And then let's see, how much is it changing by? Well, my price, by definition of my variable, my price is changing by X dollars, right? Because X represents my price reduction, so that's how much I lowered the price. And so this has to be X, just because that's the way I define my variable. And then remember when we did those tables, right? We said that if we had like a price of 10 and then we skipped to like a price of 20, that if my price, oh, sorry, my price, I'm going the wrong direction. We're going down. So if we had a price of 20 and we skipped to a price of 10, that if this went down 10, we said that the quantity had to go up 10 times, right? So for every dollar, our quantity is increasing by 8, which means to get the total increase in quantity, we have to multiply 8 by the number of dollars that we change the price, which is X. So my change in quantity is just 8 times X. So you can think of 8 as like a rate of change, right? Like, so for every $1 change in price, the quantity changes by 8. And so that gives us an expression for our new price and an expression for our new quantity. Our new price is just our old price minus the price reduction. And then our quantity is our old quantity plus the change in quantity. These problems will essentially always be set up the same way. You just have to be careful about where you put each number and sign and all that stuff. So make sure that the quantity, the change in quantity corresponds to the quantity and the change in price corresponds to the price. And it will always tell you what your X is. And so that's how you know which one is X. So that means our price per coat is 100 minus X. The number of coats sold at that price is 400 plus 8X. And then, well, revenue is always just price times quantity, right? So 100 minus X times 400 plus 8X. And I'm not going to distribute that because I don't need to. So one of the keys to this test taking 50 minutes is that we have to remember that we have ways of finding the vertex using factored form, standard form, and general form without having to manipulate the equations at all. Same with x-intercepts, right? If we set a quadratic function equal to 0, if it's in general form, we can use the quadratic formula. If it's in factored form, we can solve by factoring. If it's in standard form, we can use the square root property. So you don't have to distribute and multiply things out and get things in a different form because we have ways of finding everything we need using any one of the 3 forms. So remember that if it's in factored form, the x-coordinate of the vertex is just halfway between the x-intercepts. So if this is our revenue function, if I find the zeros, well, I just find those by setting each of my factors equal to 0. Which gives me x equals 100 and x equals negative 50. So this is negative 50 and this is 100. And if I want to find my vertex, it's going to be halfway between those. So I'm just going to average them. Remember, that's how we got the vertex formula in the first place, was we just averaged the zeros. And so my vertex, so my x-coordinate of the vertex is the average of my 2 zeros. So negative 50 plus 100 divided by 2, which is 25. And how did I know I had to find the vertex here? Instead of just some random x value.
Maximum.
Yeah, because I'm told that I want to maximize my profit. So anytime you're trying to maximize a quadratic function or minimize a quadratic function, depending on which way it opens, you're just finding the vertex. So the process for maximizing and minimizing is the same. It like which one you find just depends on which way the parabola opens, right? If it opens up, you're finding the minimum when you find the vertex. If it opens down, you're finding the maximum. So what did we just find? That 25, what is that?
The x-coordinate of the vertex.
Correct. What is it in terms of price, revenue, quantity, and everything going on with coats?
Maximum price for revenue? No. Or is that $25 less than 100 for maximum revenue? So 75.
That's exactly right. So this is the reduction in price that will result in maximum revenue. That's exactly right. So this is the reduction in price that will produce the maximum revenue. So from here, if you've set everything up for yourself, it's like answering the question, the 3 questions at the end is pretty simple. It's just a matter of going back and finding what you need, right? So if I want the price per coat, I look for price per coat, which is right there. So my price is going to be 100 minus my X value, which is 75. And then if I want the number of coats sold, I just look for the number of coats sold. And that's going to be, so that's my quantity, 400 plus 8 times 25, which is 600. And then there's a couple of ways to find the revenue. Any ideas?
Price times quantity.
Yeah. So the revenue is just the price times the quantity, and we already found a price and a quantity, right? So we could just multiply them to get the revenue. We could also evaluate our function for 25. But notice that gives us the same thing, right? Like 100 minus 25 is exactly how we got that 75. And 400 plus 8 times 25 is exactly how we got that 600. So, I mean, I could like plug 25 in all over again, but both ways I do it, I'm just multiplying 75 times 600 once we simplify that whole thing, which is like, I don't know, you guys tell me.
Oh, it's 45,000.
Thank you. So that's going to be my maximum revenue. How we doing? Okay, so let's talk housing bubble. This function, so you don't even have to write your function this time. It's given to you. So you're given this function, and I'm going to have... It's how many months? So 13 represents 13 months since whenever, January 2010, right? Is what x equals 13 is, right? But what is f, or what is v of 13?
Home value.
It's the home value at that time, right? Which, did anybody plug it in? So 180 point, we'll just say like 99. Right, so the home value, so the average home value in January of 2010 was like 180,990. If you said 181, that's totally fine. I found out in my last class that if we're too liberal with the rounding, it turns out kind of funny down here, but I mean, the numbers don't really matter here. It's mostly just what we're actually finding. So what is V of 25 minus V of 13? So anybody find V of 25?
175.875.
Let's call that maybe 88. And then we already know V of 13, right? Because we just did that. So that was 180.99. And so when you subtract them, you get negative 5.11, you said? So what does that mean?
The average price of a house went down $5,000 from January 2010 to January 2011.
Very good. So the average home value went down $5,110 from January 2010, 2010 to January 2011. What about the vertex of this function? Is it going to be a minimum or a maximum? It's going to be a minimum, right? We know that because my A is positive, and so that tells me that my parabola is going to open up. So it's going to look like something like this. And so that's my minimum. So how do we find the vertex?
Divided by 2 times.
Good, yeah, so we're using our vertex formula. Is that an 023? Yep. And that gives us, what was it, like 28.3? What do you guys get? It was 28 point something, right? We'll call it 28.3. Did I just find my vertex? Is that the vertex of this graph? Why not? Well, the vertex of a graph is a point, right? Yeah. And what did I just find? Or you just found, rather. We just found an x value, right? So we found half of it. Right? So to find a point, you have to find the x value and the y value. How do I find the y value? Yeah, just plug it into the function. So anytime you know the x value of a point and you want the y value, you just plug the x value in. So V of 28.3 is what? Like 170 something. 175.63. So this is an average home value. because it's an output, right? But what's special about this specific home value?
That's where it's gonna be the lowest.
Yeah, that's the minimum home value, right? So this is the minimum, and this is when the minimum occurred. So, average home value reached a minimum of $175,630 in, let's see, 28. Well, 25 is January 2011, so February, March, April of 2011. So just 3 months after 25, right? So 2011. Good stuff? So this last problem, we don't have time to solve the whole thing, but really what's important is just knowing what we're trying to find in each part, right? So the graph of this function, is it going to open up or down? It opens down, right? Because my A is negative. And so it's going to look something like this. So for parts A and B, I'm trying to maximize height, right? So I'm trying to find this point right here. So this is my XV and HXV. So the X value is the time that maximum height occurred, right? And then the output is what the maximum height actually was. Right, so if I find the X value of my vertex, that's going to tell me when I reached my highest point, and then plugging that into my function for height will tell me what the height was at that highest point. What about when I ask how long the stone is in the air before it hits the ground? Like, what point am I looking for on this graph? Yeah, we're looking for the x-intercept, right? You can, I mean, when you draw these graphs of these projectile problems, like the parabola is actually like the graph of like what it, if you could slow down the path of the ball, like it's what it would look like, right? So like when it hits the ground is exactly when it looks like it actually hits the ground, right? When it touches that x-axis, because that's where your height is 0. So that's what you're finding there. So sometimes just sketching a little graph can help you kind of figure out what exactly you're trying to find, because you can see it a little bit easier. So tonight,